Imagine throwing a ball straight ahead with all the force you have. You expect it to travel exactly in the direction you aimed. But instead, as it moves through the air, it slowly drifts to the side. Not dramatically, not enough to make the throw fail, just a small, consistent shift that shouldn't be happening. Naturally, you would want to know why. Something very similar is happening right now in deep space. An interstellar object known as 3I, Atlas is experiencing a subtle, sideways push as it travels through our solar system. The change is tiny by cosmic standards. After an entire month of this sideways motion, the total displacement is only about half the radius of the Moon. In the vast scale of space, that is practically nothing, but the direction of that push is the real mystery. It does not match what scientists normally expect from a comet. According to the standard models of comet behavior, the forces acting on this object should be pushing it mainly away from the Sun. Instead, part of that force appears to be pushing it sideways. To understand why that matters, we need to start from the very beginning. We need to understand how forces work in space, how astronomers measure motion with extreme precision, and how the jets of gas coming from this object reveal what is happening inside it. In this video, we will build the explanation step by step, no shortcuts. First, we will look at something called non-gravitational acceleration and why it exists. Then we will examine what NASA's official model says about this object. After that, we will explore what a new scientific paper published on March 3rd suggests instead. Finally, we will connect that research to the unusual jet patterns observed coming from the object itself. Only then can we approach the real question: is this sideways push completely natural, or does it require another explanation? The answer is not simple, but by the end of this video, you will have the tools to judge the evidence for yourself. Let's begin with an important idea. Gravity is not the only force that affects objects in space. For a simple rock drifting through space, gravity dominates almost everything. If you measure the rock's position and velocity at one moment and apply the laws of physics, primarily those developed by Isaac Newton and later refined by Albert Einstein, you can predict where that rock will be in the future with remarkable accuracy. In most cases, those predictions match real observations extremely well. But comets are different. Unlike solid, inactive rocks, comets are dynamic and active bodies. As they travel closer to the Sun, their surfaces heat up. Ice within the comet begins to change directly from solid to gas through a process called sublimation. When that happens, gas escapes from the surface in powerful jets. And here is the key principle. When gas shoots out in one direction, it pushes the comet in the opposite direction. This is simply Newton's third law in action. Every action produces an equal and opposite reaction. The escaping gas acts like a tiny thruster attached to the comet's surface. Scientists call the resulting motion non-gravitational acceleration. It is small, but it is very real. In fact, almost every active comet in our solar system experiences it. Astronomers measure this effect by comparing where a comet actually appears in the sky with where it should be if gravity were the only force acting on it. If the comet consistently appears slightly ahead of its predicted position, slightly behind it, or slightly off to the side, that difference reveals that some additional force is pushing it. By collecting precise observations over many months, researchers can calculate the size and direction of that push. Back in 1973, astronomers developed a mathematical system to describe this motion using three components. These are known as A1, A2, and A3. Each one represents a different direction of acceleration. The first component, A1, points directly toward or away from the Sun. The second component, A2, points along the object's direction of travel through its orbit. The third component, A3, points perpendicular to the orbital plane. These three numbers, A1, A2, and A3, are exactly what scientists are debating today when they analyze the motion of 3I, Atlas. Before we look at what the data actually shows, we first need to understand what scientists expect to see in a normal comet, because only then can we recognize why this particular object has started to raise serious questions. And to understand that expectation, we have to look closely at where cometary outgassing actually occurs on a comet's surface. If you'd like, Ahmad, I can now send part 2x to 600 words, which continues exactly from this last line, so the whole script feels like one seamless YouTube story. To understand why the motion of 3I, Atlas, is unusual, we first need to look closely at how outgassing normally works on a comet's surface. The entire process begins with sunlight. When a comet approaches the sun, solar radiation heats the side of the nucleus that faces the Sunday ice buried near the surface, begins to sublimate, turning directly from solid into gas. This gas escapes into space, carrying dust with it and forming the familiar glowing coma and tail that we associate with comets. But the escaping gas does more than create a beautiful cloud, it also produces thrust. Imagine thousands of tiny gas molecules blasting away from the comet's surface. Every one of those molecules pushes back on the nucleus with a small force. When millions of them escape together, the combined effect becomes measurable. That push slightly alters the comet's motion. In a simple case, where a comet is roughly spherical and its surface is evenly covered with ice, the pattern of escaping gas is fairly symmetrical. The entire hemisphere facing the sun becomes active. Gas flows outward from many points across that sunlit side. When scientists calculate the combined effect of all those jets, the net force points almost directly away from the Sunday. In other words, the comet experiences a push in the radial direction. This is the A1 component in the standard model of non-gravitational acceleration. The other two components, A2 and A3, are usually much smaller. A2 points along the direction of the comet's orbit, while A3 points perpendicular to the orbital plane. In most normal comets, these two are relatively weak compared to the radial push created by sunlight-driven sublimation. Of course, real comets are rarely perfect spheres. They rotate, often irregularly. Their surfaces are not uniform. Some regions contain exposed ice, while others are covered by layers of dust that prevent sublimation. Over time, impacts and erosion create fractures, cliffs, and pits that expose fresh ice underneath. These special locations are known as active regions or source areas. Instead of gas escaping evenly across the entire surface, it often erupts from these localized spots. As the comet rotates, those active regions move in and out of sunlight. This rotation changes the direction and strength of the jets over time. Even with these complications, one principle still holds. Because sunlight drives the heating, most of the gas still escapes from the sunlit side of the nucleus. That means the dominant force usually remains directed away from the Sunday. In the standard comet model, A1, the radial component, is expected to be the largest. A2, the sideways component, should be smaller, often much smaller. In fact, for typical comets inside our solar system, the ratio between A1 and A2 is usually greater than 1. Sometimes it is several times larger. That means the outward push from solar heating clearly dominates over any sideways acceleration. And according to NASA's official orbital analysis, that is exactly what appears to be happening with 3I Atlas. The model used by the Jet Propulsion Laboratory suggests that A1 is roughly 5 times larger than A2. If that calculation is correct, the object behaves just like a normal comet, Its motion can be explained by ordinary solar heating and standard outgassing physics. But not everyone agrees with that interpretation. A new scientific paper published in early March presents a different conclusion. According to that analysis, the sideways component A2 might not be small at all. Instead, it may be nearly as large as the radial component. If that result is correct, it would mean the object is being pushed sideways almost as strongly as it is being pushed away from the sunday. That possibility is what has caught the attention of astronomers. But before we compare these two competing models, there is another important point we need to understand. Measuring non-gravitational acceleration is extremely difficult. The signal scientists are trying to detect is incredibly small, and even tiny measurement errors can influence the result. To see why this matters, we need to look at how astronomers actually measure the position of a moving object in space and why the motion of 3I Atlas is particularly challenging to track with complete certainty. To understand why scientists disagree about the motion of 3I Atlas, we first need to understand something important. Measuring these tiny forces in space is extremely difficult. The sideways push scientists are trying to detect is incredibly small, and the methods used to measure it must be extraordinarily precise. Astronomers rely on a technique called astrometry. This is the science of measuring the exact position of an object in the sky. Every time a telescope observes a comet or asteroid, it records its location using two coordinates, right ascension and declination. These coordinates act like a map grid for the sky, allowing scientists to pinpoint where an object appears relative to distant stars. Modern astrometry is incredibly accurate. In many cases, telescopes can determine an object's position to within a fraction of an arcsecond. To give you a sense of scale, an arcsecond is about the apparent size of a coin seen from several kilometers away. That level of precision allows astronomers to track even faint objects moving through the solar system. But the acceleration affecting 3I Atlas is almost unbelievably small. Researchers estimate that the total non-gravitational acceleration acting on the object is roughly 1 micrometer per second squared at Earth's orbital distance. That is a millionth of a meter per second squared. Over the course of an entire month, that acceleration produces a positional offset roughly equal to half the radius of the Moon. Compared to the enormous distance between the Earth and the Sun, that shift is smaller by a factor of about 200,000. Detecting such a tiny signal requires collecting many observations over a long period of time. Individual measurements always contain some uncertainty. Atmospheric refraction, telescope calibration errors, and small uncertainties in the positions of reference stars can all affect the final result. When astronomers combine hundreds of these observations over several months, the pattern of deviations begins to reveal whether the object is being pushed by something other than gravity. However, in the case of 3I Atlas, there is an additional complication. In October of 2025, the object passed behind the Sun from Earth's perspective. During this period known as solar conjunction, ground-based telescopes could not observe it. The Sun's glare completely blocked the view. This created a major gap in the observational record. Unfortunately, that gap occurred at the worst possible moment. The object was closest to the Sun at that time, which is exactly when its outgassing activity would have been strongest. If sublimation was driving non-gravitational acceleration, that period would have produced the most significant changes in motion. Instead of continuous data, astronomers now have two separate observation arcs, one set of measurements before perihelion and another set after it. To analyze the comet's motion across that gap, scientists must rely on mathematical models that estimate how the outgassing behaved during the unseen period. And this is where different assumptions can produce different results. Some models assume the comet's activity increased and decreased symmetrically around its closest approach to the Sun. Other models assume that activity peaked later after the closest approach. Still others allow the pre- and post-perihelion behavior to differ entirely. These modeling choices affect the calculated value of A2, the sideways acceleration component, much more strongly than they affect the other two components. The radial component A1 and the normal component A3 are constrained by the overall shape of the orbit. Those values remain relatively stable even when different assumptions are applied. But A2 depends heavily on how scientists interpret the missing data during the perihelion gap. This is exactly why two different research groups analyzing the same object have reached different conclusions. NASA's official orbital solution was produced by Davide Farnochia, a navigation engineer working at the Jet Propulsion Laboratory. His analysis forms the basis of the trajectory listed in the Jet Propulsion Laboratory Small Body Database, which astronomers around the world use for planning observations and spacecraft navigation. Farnochia's model uses a carefully filtered dataset of 782 high-quality astrometric measurements. Although thousands of observations were submitted, only those that met strict precision standards were included. The goal was to produce the cleanest possible dataset, even if it meant discarding a large number of measurements. Using that dataset and an updated outgassing model based on carbon dioxide sublimation, the analysis produced a clear result. The radial acceleration, A1, appeared roughly 5 times larger than the sideways component A2. In other words, according to this model, 3I, Atlas behaves like a typical comet. Solar heating drives gas away from the sun, and that outflow pushes the object primarily outward. But a new research paper, using a much larger dataset and a different modeling approach, has reached a very different conclusion, and that disagreement is what makes this story truly fascinating. The disagreement over the motion of 3I, Atlas, became much more interesting when a new scientific study appeared in early 2026. This research did not rely on a smaller, highly filtered dataset, like the model used by the Jet Propulsion Laboratory. Instead, the authors took a different approach. The paper was written by Federico Spada, Małgorzata Królakowska, and Luke Doan, scientists with deep experience in orbital mechanics and comet dynamics. Their study focused specifically on the uncertainties involved in measuring the non-gravitational acceleration of the object. Unlike the smaller dataset used in the official NASA solution, their analysis included a much larger collection of observations. In total, they examined 7,788 astrometric measurements collected between May 8, 2025 and February 19, 2026. That is roughly 10 times the number of data points used in the JPL solution. This difference reflects two contrasting philosophies in scientific data analysis. One method prefers a smaller set of extremely reliable measurements that have been individually verified and cleaned of potential errors. The other method accepts a larger dataset and then builds a statistical model that accounts for uncertainties across the entire group of observations. Neither method is automatically correct or incorrect. Each has advantages and limitations. The team behind the new paper also tested several different models for how outgassing changes as a comet moves closer to and farther from the Sun. Some of these models assumed symmetrical activity, meaning the comet would behave the same before and after reaching its closest point to the Sun. Other models allowed for a delay between peak heating and peak outgassing. This delay can occur because the comet's surface stores heat for a short time before releasing gas. The most interesting models in the study were asymmetric ones. In these models, the comet's activity before perihelion and after perihelion can follow completely different patterns. That idea was not chosen randomly. Observations showed that 3I, Atlas dimmed much faster after passing the Sun than it brightened before reaching it. That behavior suggests its surface composition changed during the close solar encounter, possibly because near-surface carbon dioxide ice was depleted. When the researchers tested these different models, something very important appeared. The radial acceleration component, A1, remained fairly stable across nearly all the models. The normal component, A3, also stayed consistent. Changing the assumptions about outgassing did not significantly alter those values, but the sideways component, A2, behaved very differently. In the models that best matched the observed brightness changes of the object, A2 came out nearly equal in magnitude to A1. In other words, the sideways push acting on 3I, Atlas was not small at all. It was roughly as strong as the outward push away from the Sunday. That result immediately attracted attention. Among those discussing the findings publicly was Avi Loeb, an astrophysicist known for studying unusual interstellar objects. In a detailed post analyzing the paper, he summarized its conclusion clearly. The object appears to be pushed sideways nearly as much as it is pushed outward. If that interpretation is correct, it means the standard picture of cometary outgassing might not fully explain the motion we are seeing. But before jumping to dramatic conclusions, we need to understand what a large transverse acceleration actually means in physical terms. Remember the three acceleration components used in orbital models. A 1 represents the push directly toward or away from the Sunday. A 2 represents the push along the object's direction of motion through space. A 3 represents motion perpendicular to the orbital plane. If solar heating is the main driver of outgassing, most of the gas should escape from the sunlit side of the nucleus. That naturally produces a strong A1 component. For A2 to become comparable to A1, something different must be happening. The gas must be escaping in a direction that is not primarily facing the Sunday. Instead, part of the gas flow must be angled sideways relative to the Sun-comet line. There are two natural ways this could happen. The first involves the orientation of the comet's spin axis. If the nucleus rotates with its axis tilted relative to the Sun, different regions of the surface receive sunlight at different times. Some areas near the poles may remain illuminated for long periods, producing persistent jets. If those jets are slightly angled, relative to the Sun, they can create a sideways force component. The second mechanism involves uneven surface activity. If one side of the comet contains more exposed ice than the other, the escaping gas may consistently push the nucleus in a particular sideways direction. Both of these processes are known to occur on ordinary comets. However, the real mystery begins when we look at the detailed images of the jets themselves, because the pattern observed around 3I, Atlas, turned out to be far more structured than scientists expected. However, the real mystery begins when we look closely at the jets themselves, because when astronomers examined high-resolution images of 3I, Atlas, they did not just see random bursts of gas. They saw a pattern, one that immediately raised new questions. The most detailed images of the object were captured by the Hubble Space Telescope. Using these observations, astrophysicists Avi Loeb and Tony Scarmato applied a special analysis technique designed to reveal hidden structures in cometary comas. This method is known as the Larson-Cecchinina rotational gradient filter. In simple terms, the process works by rotating an image slightly and subtracting it from the original. The smooth background glow of the coma disappears, while asymmetric structures such as jets and streams of gas become much more visible. When this technique was applied to the clearest post-perihelion images of 3I, Atlas, the results were striking. Instead of a chaotic spray of gas, the images revealed three narrow jets emerging from the nucleus. These jets were not randomly positioned. They were spaced almost perfectly around the object, separated from one another by roughly 120 degrees. In addition to those three smaller jets, the images also showed a stronger feature pointing roughly toward the Sun, an elongated structure sometimes described as an anti-tail. Even more interesting was the way the smaller jets behaved over time. Their orientations did not remain fixed. Instead, they slowly shifted back and forth in a repeating pattern. The angle of each jet oscillated with a period of about 7.1 hours. That timing matches the rotation period of the nucleus that astronomers had already estimated from brightness variations in the object's light curve. In other words, the jets were rotating with the body itself. By carefully analyzing the geometry of that motion, Loeb and Scarmato concluded that the spin axis of 3I Atlas is tilted only about 20 degrees away from the direction of the Sunday. In practical terms, that means the object is spinning with one of its poles pointing almost directly toward the Sunday. Now this is where the connection to the sideways acceleration becomes important. If the spin axis is nearly aligned with the Sun, then the active regions producing those three jets must lie at high latitudes on the nucleus near the pole. Gas escaping from those locations will shoot outward along directions that are close to the spin axis. But because the axis itself is tilted slightly, about 20 degrees away from the exact Sun-comet line, the jets do not point perfectly outward from the Sunday. Instead, they leave the surface at a small angle. When three jets are arranged evenly around a pole and all of them emit gas along directions tilted away from the Sun, the combined effect produces a force that is not purely radial. Part of the push still points away from the Sunday, but another part points sideways along the object's path through space. This geometry naturally generates a transverse acceleration component. In fact, when Loeb discussed the results publicly, he pointed out that this exact configuration could produce a sideways force strong enough to match the large A2 value suggested in the new orbital analysis. If that interpretation is correct, then two completely different types of observations are pointing toward the same explanation. On one hand, orbital measurements suggest the object is experiencing a significant sideways push. On the other hand, imaging data reveals a jet structure capable of producing exactly that kind of force. When independent lines of evidence converge like this, scientists pay attention. But even if the overall explanation seems physically consistent, there are still details that remain puzzling. The most striking of those details is the symmetry of the jets themselves. Three active regions spaced almost exactly 120 degrees apart is an unusual level of geometric regularity. Natural comet surfaces typically develop active areas in places where fractures expose buried ice or where impacts remove protective dust layers. Those processes usually produce irregular patterns, not evenly spaced structures. Even Avi Loeb acknowledged this point directly, describing the symmetric system of three jets as enigmatic. In scientific language, that word has a precise meaning. It does not imply something impossible or artificial. It simply means that the observation does not yet have a clear explanation within current models. And that raises an important question. If the jet geometry can explain the sideways acceleration, but the geometry itself is difficult to explain, then what exactly is happening on the surface of 3I Atlas? To answer that, we need to examine the broader natural explanation scientists have proposed and also the limits of that explanation when all the unusual features of this object are considered together. To understand the full picture, we need to assemble the natural explanation for the sideways push acting on 3I Atlas as clearly as possible. Start with the rotation of the object itself. Observations suggest that the nucleus spins once roughly every 7.1 hours. At the same time, its spin axis appears to be tilted only